Welcome back, fellow mitochondriacs, for another episode of Cancer is a Mitochondrial Metabolic Disease. I am happy to be back today to kind of finish out finally the most recent Seyfried paper. I've dedicated, I think now about 4 videos to it, and the last piece of it is probably going to be the least novel for us, just because obviously if you're here, you have already at least been exposed to the fact that cancer could be a mitochondrial metabolic disease, if not fully accepted it. So let me share my screen here. Give me 1 second, you guys. So I think I'm having a bit of a technical difficulty. I got a new computer here, and it's making me gonna have to restart Chrome in order to share my slides, which is a problem because I think that'll kill the live stream, you guys. Let's do this. I'm gonna come right back onto the same link. Give me 2 minutes to fix the issue, and I'll be back. Stand by. All right, this will be attempt number 2. All right, looks like this could be the ticket. All right, so we left off on questionable number 7 on the prior video. And I think that is really important to cover because it really hammers these questionable assumptions that are made throughout cancer biology and oncology. And I think that we probably covered those pretty well. But what we did not cover yet is the last 3 kind of subtopics within this new paper that was published. And it was cancer as a mitochondrial metabolic disease, therapeutic implications, as well as their conclusions. So let's get into it. So it said, we, like Warburg, consider the origin of energy ATP production as a central issue in cancer. Without energy, no cell can remain viable or synthesize metabolites regardless of gene mutations or their connected signaling cascades. So I want to take a pause here because this is really the key issue that I think has to be highlighted over and over again, because even though these cells may have gene mutations, they may have aberrant signaling cascades. For example, the AKT, PIK3, mTOR pathway, or a VEGF, or some kind of a growth signaling pathway like HER2, any of those type of signaling pathways, what do they ultimately do? We've looked at this over and over again. They upregulate glucose and glutamine somehow, because ultimately, like it says here, the central issue is is that if there's no energy, it doesn't matter, because basically you're not going to be able to like make new things, aka in this case synthesize metabolites. Like you can't build a house if there's no workers. So, and it doesn't matter, if in this case, trying to continue the analogy, the signaling cascades that like upregulate the materials. But if there's no workers, it doesn't matter how much money is spent or how much influence you try to put on the company, the house building company. If there's no workers, that's not going to get done. And that's kind of like the central argument that Warburg before him and Seyfried is trying to make. And I think it's an excellent argument, because ultimately everything in that's alive requires energy. And if you don't have that, then therefore it doesn't matter what else is going on around it. It's going to collapse. Going further, it says decreased ATP production in a cell by any means will cause the loss of the potassium and gain sodium and calcium, and if persistent, to decrease voltage, altered volume, and cell death. So what he's talking about here is the sodium potassium ATPase, and it runs on, as you would imagine, ATP. And if you lose that, you will have decreased voltage across the membrane, it'll alter volume, and it'll ultimately lead to cell death. So again, underscoring the need, the central role for energy for cells to remain alive. According to traditional biochemistry, there are two primary mechanisms for producing cellular ATP. These include OXPHOS, or oxidative phosphorylation, energy that requires oxygen and goes through the functional electron transport chain in a mitochondria, and substrate level phosphorylation. The amount of ATP produced through OXPHOS is also linked to the structure and the membrane protein/lipid composition of the cristae and the inner and outer mitochondrial membranes. So this is probably one of my more favorite things to talk about, although I can understand that it's somewhat esoteric. But what he's saying here is what I talk about quite often. So the architecture of the actual membrane. So he's talking about the inner membrane space here, which is between the outer membrane and the inner membrane. This is where the hydrogen protons are pumped to. And this is the mitochondrial matrix out here where the mitochondrial DNA is at. And here is the cytochrome proteins. And these cristae, these enfoldings of the membrane, are critical for OXPHOS. You can see here that it's kind of like showing it here, where you see it's not very easy to see probably on maybe a smaller screen, but you see here where there's membrane foldings that are all over the place. And then you see one that's not, right? You see this is like a more vacuolated looking mitochondria. Well, you can see here that the mitochondrial proteins are really close together when the membrane cristae are intact, which means there's going to be efficient oxidative phosphorylation, and there'll be very little or physiologic amounts of reactive oxygen species, which we know are not all bad. They participate in signaling and stuff like that. But when the cristae are unfolded and there is like a vacuolated looking mitochondria, all the mitochondrial proteins will spread out. Well, what does that functionally do? It leads to lack of ATP production, and it leads to more reactive oxygen species, which damages membranes and kind of like feeds forward this mechanism. If it wasn't just the membranes, it also damages the mitochondrial DNA. And if it's catastrophic enough, if it's severe of a defect enough, what will happen is mitochondrial DNA or cytochrome C will be ejected from the mitochondria, and it'll allow for apoptosis. So it is my thought that the reason why cancer shuts down mitochondria at a certain point through hypoxia-inducible factors and stuff like that is because it's trying to prevent this from happening. It's trying to prevent mitochondrial DNA and cytochrome C from happening and being ejected and activating apoptosis. So that's how the cancer cell is able to overtake programmed cell death, because they shut down mitochondrial function. Another way of looking at this is, and what I was showing here is kind of like a picture of the mitochondrial supercomplex. The mitochondrial supercomplex looks like this when it's like, look at its crystalline structure under an electron micrograph. But when it's separated, you have more ROS production. And then that kind of like is a vicious cycle, like it says here, because it's going to damage lipid membranes, going to destabilize complex 1, and it's going to be a forward feed mechanism that leads to more and more problems. And it's better shown here probably like as the gestalt, because you have a loss of supercomplex organization, you have inefficient electron transfer, you have decreased OXPHOS, and then that inefficient electron transfer leads to oxidative stress within the membranes, within the mitochondrial DNA. That leads to membrane lipid peroxidation, and cristae will fall apart especially when cardiolipin, a very important membrane, is oxidized, and then you lose more supercomplex, and then it becomes like a vicious cycle that leads to what we're talking about here. So that's what Seyfried's saying here. It's he's saying that the amount of ATP produced through OXPHOS is also linked to the structure and the protein and lipid composition of the cristae and the inner and outer mitochondrial membrane proteins. That's what he's basically saying in a very short amount of time without kind of like expanding what I was doing there. So later in the paper, in the same section, it says, under hypoxic conditions, however, most of the pyruvate is metabolized to lactate, while some of the succinate leaves the TCA cycle as both a metabolite. Metabolites are produced as waste products of glucose-driven glycolysis and glutamine-driven glutaminalysis pathways, respectively. Hence, the mechanism of ATP production in the presence of oxygen is predominant difference between cancerous cells and non-cancerous cells. So again, the central thesis behind genetic theory of cancer is that these altered genes are upregulating all of the machinery necessary for these cells to replicate out of control. But the big but here is that they believe, or most believe, that OXPHOS is still intact. And what Seyfried is saying here is that under low oxygen conditions, most pyruvate is going to be fermented to lactate. Pyruvate is the end product of glycolysis. And some of the succinate is the end product of the fermentation of glutamine, leaves the TCA cycle as both metabolites are produced by waste products of glucose and glutamine-driven glutaminalysis pathways, respectively. Hence, the mechanism of ATP production in the presence of oxygen is the predominant difference. So when oxygen is present, normal cells will always prioritize the use of OXPHOS because it's much more of an efficient process, and the cell remains in control of all kinds of important things like programmed cell death, like gene expression. When you lose control of that, then it can grow out of control, and you end up with these toxic waste products, the succinic acid when it's in excess, or the lactic acid when it's in excess. So what they're saying, and what Warburg was saying, is that the mechanism of ATP production, the way ATP or energy is produced in the presence of oxygen, when oxygen is present, is truly the predominant difference between a cancer cell and a normal cell. Hope that makes sense. I'm going to greet some people here for a second. Hello, Noel. Hello, Paul. Thank you. Good afternoon. It is afternoon here. It must be evening over there. So it further says that cancer is rare in cells that cannot chronically replace ATP production through OXPHOS with ATP production through substrate level phosphorylation. Examples would be post-mitotic cardiac myocytes or heart muscle cells and brain neurons. While these cells can rapidly upregulate ATP production through mitochondrial or through substrate level phosphorylation under acute oxygen deficiencies, aka cardiac arrest, aka epileptic seizures, they cannot sustain this ATP production for more than a few minutes without suffering catastrophic death, thus preventing a protracted transition to substrate level phosphorylation. In contrast to the transient accumulation of lactate and succinate under hypoxia in normal cells, the waste product of glucose and glutamine fermentation continue to accumulate in cancer cells even in the presence of oxygen. The persistent extracellular accumulation of lactate and succinate together with the cytoplasmic accumulation of lipid droplets in cancer result in large part from the well-documented abnormalities in number, structure, and function of mitochondria. It should be recognized that mitochondrial proton motive force controls calcium signaling, which regulates the cyclins, the cell cycle, and the quiescent and differentiated state of the cell. So a couple other important things here. So basically what they're saying is that the normal kind of state of the cell is quiescence. It's not rapidly dividing. And so when you lose I'm trying to find a graphic here. I don't have one that's fantastic here, but the bottom line is when you lose the membrane, it said proton motive force. Basically, when you lose the ability to concentrate protons or hydrogen ions in the inner mitochondrial membrane space, and that proton gradient is what leads to the making of ATP through the ATPase. When you lose that, you lose control of some very important things, one of which is calcium signaling, and that regulates the cell cycle. So basically, when you lose control of the cell cycle, you can have dysregulated cell growth, and that's why mitochondrial dysfunction can lead to cancer in above and beyond the loss of ATP, because basically you're losing one of your major controllers. The other thing that is not mentioned here is that when mitochondria are not like kind of terminally damaged, again, you're not going to eject mitochondrial DNA. You're not going to inject cytochrome C. So therefore, you also lose control over programmed cell death and apoptosis as well. It further says, in other words, it is the efficiency of OXPHOS that maintains the differentiated state of somatic cells, while the chronic loss of OXPHOS efficiency leads to substrate level phosphorylation driven dysregulated cell growth, aka neoplasia, aka cancer. We also solved St. George's oncogenic paradox in showing that chronic OXPHOS insufficiency coupled to increased substrate level phosphorylation is the common pathophysiologic mechanism linking malignant transformation to a broad range of unspecified influences, including age, intermittent hypoxia, carcinogens, localized and systemic inflammation, radiation, rare germline mutations, oncogenic viruses, etc. And it says, hence, a greater dependency on substrate level phosphorylation than on OXPHOS for energy is the pathophysiologic phenotype common to all major cancers. And then I can't remember if I've showed this graphic in this video series or not, but this is like the updated version of their, what I consider a very classic graphic that I've shown multiple times. And what we see here, I think the most important, well, maybe I'll start here. So we see that in normal cells, the majority of energy is made through ATP or through oxidative phosphorylation or through the electron transport chain in a functional mitochondria. Then what happens is over time, you have a gradual loss in OXPHOS and you have a gradual increase in substrate level phosphorylation. What they were saying in the last couple of slides was basically that neurons, brain cells, and post-mitotic cardiac muscle cells or myocytes are not able to participate in that, which is why you never see cancers in neurons or in heart myocardium, like muscle tissues. You may say, well, there's brain cancers. Yes, but those are astrocytes. Those are like other supporting cells to the brains, not the actual neurons. So what we're seeing here is a gradual loss of OXPHOS right here in green. So energy from ATP from mitochondria is gradually decreasing. There's a transformation event here. So there is going to be some level of crossover. But what the argument is that in the absence of fermentable fuels, this amount is not enough to keep the cells alive. They need this, right? They need 100%. And if they're only getting 40%, it's not enough. So this would be like a pre-cancer, early cancer, and then like a real, malignant tumor here that's detectable probably on a PET or some kind of a tumor marker or something like that would be over on this side of it. We see here a gradual increase in SLP by the red, substrate level phosphorylation, or that would be the fermentation of glucose and glutamine, right? There's another name for that, Warburg metabolism, which is generally the substrate level phosphorylation of glucose, is also kind of like another misnomer or another name for that. So the second thing that I see here, well, actually, I'm going to say here, see how these mitochondria have like beautiful cristae looking, and these are like vacuolated? That's what they're showing here. Here's like one extreme. There's like beautiful mitochondria with wonderful cristae and wonderful ATP production. And then we have like the other extreme here, right? Which is like insufficient oxphos, increased SLP. So these are the extremes here and here. And then you're going to have like phenotypes or like that looks like this, right? Like you're going to worst looking cristae, and ultimately somewhere in here, see there's a T here, there's transformation. So what is new about this graphic, because this is pretty much here, is that you have new kind of bubbles here in the pink, I guess you'd call them, or kind of salmon colored, where you have forever chemicals, carcinogens, hypoxia, radiation, age, rare, germline, or kind of inherited mutations, and then viruses, inflammation, microplastics. I think I would, first of all, this is not an exhaustive list, and I'm not saying that they're saying this is an exhaustive list, but some things that I think, they're kind of adding in kind of like modern things, right? Forever chemicals, microplastics, but I would also just as easily in here put light, the light that you are supposed to get that you're not getting, and the light that you are getting that you're not supposed to be getting at the right part of the day and the wrong part of the day, because that's going to affect vitamin D. It's going to affect melatonin. And when you have those, you do not have adequate protection of mitochondria. Then the next thing you're going to see here is you're going to see ROS, right? ROS, reactive oxygen species, superoxide, the hydroxyl radical here. And so ROS, it makes it seem on this graph that it's affecting only the nuclear DNA and leading to genomic instability, which it's not only affecting it, it's also going to feed back on the place where the reactive oxygen species are the most proximal, right? So the electron transport chain is here in the mitochondrial membrane, and the mitochondrial membrane is right next to the mitochondrial DNA. So it's going to also, at the same time, it's not going to just create reactive oxygen species and damage nuclear DNA. It's also going to damage mitochondrial DNA. And those mitochondrial DNA encode for the very proteins that are on the mitochondrial electron transport chain, which makes them more inefficient, more leaky of electrons, and it feeds forward this whole mechanism. It's also going to damage the inner mitochondrial and outer mitochondrial membranes and have lipid peroxidation. And that's going to lead to falling apart of the cristae even further. In fact, I mentioned this once, that cardiolipin is one of the critical membrane fats that are in the inner mitochondrial membrane. And when cardiolipin is absent, the membrane will fall apart. And when cardiolipin is present, it will form, much more likely to form the electron, or excuse me, the cristae, and the supercomplexes can more likely form. When there's ROS, cardiolipin is peroxidized, or it's oxidized basically, and then this will fall apart. So this is kind of how it happens over time. It's not generally an acute thing. If it was an acute thing and it was severe enough, it would just lead to the ejection of mitochondrial DNA and cytochrome C, which will actually just kill off the cell through apoptosis. But it's a gradual thing, and so that's how I'm kind of like looking at this. And then what happens is you see here, HIF1 alpha, c-Myc, these are oncogenes, and these are things that are activated. Well, at least HIF1, I can say, is activated by several things that we've talked about over and over again. I have a whole kind of 3-part series about HIF1 alpha, and I've even learned quite a bit about HIF1 alpha since those videos came out. But it can be activated by ROS, and when HIF is stabilized, then it upregulates all of the machinery necessary for both cytosolic and mitochondrial substrate level phosphorylation. And so that's how it's set up. A couple other things that are kind of maybe not well shown here is that you could also argue that when substrate level phosphorylation is happening, you're going to evade immune, I don't know if it says here, but it's going to evade the immune system because of all the lactate and the succinate. It's going to set up the external shields around the cell. But anyway, it's a pretty awesome graphic, and it really just kind of like underscores like the main kind of like points that are made over and over again in the words, but it really kind of brings them to life, in my opinion. So that leads us to, and I'm skipping quite a few things because it's going to be covered again, but that leads us to the therapeutic implications, right? And therapeutic implications are really what most of us, whether we're a clinician, or if we're on the other end of a diagnosis, or we are on the other end of sitting next to a family member or a friend who's got a diagnosis, really, really care about. So the reason why I personally go into all this detail is because it's critical for me that you understand the importance of what we're doing and why we're doing it. Because when we, look at a graphic that looks like this was the kind of the classic Seyfried graphic that was from the 2017 Press Pulse paper. And when you see this, after what we've explained in all the videos that have led up to this, when we, and in particular, the last videos talking about this particular problem, covering this entire paper, covering the kind of digressions into does cancer use ketones for fuel, et cetera. But my point is that when you understand that glucose is upregulated to 10 to 30x more to be able, and glutamine also is upregulated 10 to 30x more in these cancer cells compared to their normal counterparts. And the reason is because it's upregulating substrate level phosphorylation to make up for that energy loss of oxphos. It makes more sense that those would be there, right? When we go over, for example, that no other amino acid can replace glutamine, it makes sense why glutamine inhibition would be here, right? So this starts to make a heck of a lot more sense when you understand what's really going on. And what I'll also tell you is that when you're doing metabolic therapy, ketogenic metabolic therapy, or attempting to do ketogenic metabolic therapy, it is probably changing every part of your life because you're on a therapeutic diet, therapeutic ketogenic diet. You're tracking calories, you're tracking macros, you're doing stress reduction. You're like trying to find, different things that can inhibit glucose or glutamine and get your hands on it and who can help me with it. And so your entire world becomes about these things, right? And then, this is something that I did talk to Dr. Seyfried recently about in our podcast, and it'll be up Monday, by the way, at least the first half of it. I kind of found a decent stopping part, because it's about 2 hours long, and I wanted it to be broken up at least two. What I may do is after I post the entire thing, I may just post both parts. I may just post a big one for people who like longer form, like very long form, kind of type videos. But anyway, I pressed him on this because the HBOT is present as a pulse therapy in the 2017 paper, and in the 2024 December paper, he has a graphic that looks like this and subsequently like this, and HBOT is not really talked about at all. And I'll let you listen to his answer about why that is, or whether or not it's required or not. But my point is that when you're in a difficult situation of a diagnosis like cancer, and you're in a very difficult situation of trying to change your entire life and do all these things and learn all these things and really start to like be implementing this therapy, it's very difficult. And if you don't understand the importance and why we're doing what we're doing, then it's going to be I have to imagine, like human nature, it'd be much easier to give up, if you don't understand the critical nature of these two, of glucose and glutamine, for the importance of cancer and metabolism and how it is the dominant way these cancer cells make energy, right? So that's why I like to go into the detail. I also like to know why I would, even consider using this as a therapy if there doesn't make any biologic sense. So going forward, it's saying therapeutic implications. According to the American Cancer Society, almost 612,000 people are projected to die from cancer in the US in 2024. Wow. Which amounts to about 1,700 people dying per day or 70 people dying per hour. The anti-smoking campaign of the 1990s was largely responsible for preventing the number of yearly cancer deaths from being even higher. The failure to reduce cancer deaths results in large part from the persistent belief that cancer is a genetic disease. According to the somatic mutation theory, the press-pulse therapeutic strategy for cancer management was developed based on a new understanding that cancer is a disorder of mitochondrial energy metabolism. The strategy involves the simultaneous restriction of glucose and glutamine while the body is placed in a state of nutritional ketosis. The ketone body beta-hydroxybutyrate has been designated a superfuel because it A, does not uncouple the mitochondrial electrochemical gradient like fatty acids, and thus increases delta G of ATP hydrolysis. B, has more carbon hydrogen bonds than pyruvate. C, produces few oxygen radicals during its metabolism. D, can replace glucose as energy source for the brain and other organs. Indeed, Dendrick and co-workers showed that glucose concentrations as low as 0.5 millimoles per liter, aka 9 milligrams per ml, failed to precipitate hypoglycemic reaction in insulin-treated subjects when their circulating levels of beta-hydroxybutyrate was elevated. That's unbelievable. I have personally never seen anyone's glucose of 9 that wasn't having basically like a near-death experience, because most people who end up with a glucose of 9 are people who like overdo insulin or like a medication that's like a pathophysiologic issue, and they don't have ketones in their system because it's such an acute change. So they're in bad shape. So when I see a number like that, I'm just frankly shocked that is even like possible, that humans, as long as they have high levels of ketone bodies, they can tolerate that and like not show any hypoglycemic symptoms. That is very hard for me to believe, but Drennick et al. In 1972 apparently found that. The whole body transition from glucose to ketone bodies will reduce the ability of glucose to both the glycolytic and pentose phosphate pathways, while also consuming some of the CoA needed for driving substrate level phosphorylation. Hence, the reduction of circulating glucose and elevated ketone bodies will deprive tumor cells of energy and the glucose carbons needed for the synthesis of growth metabolites. Press-pulse ketogenic metabolic therapy, KMT, involves the simultaneous targeting of cytosolic and mitochondrial substrate level phosphorylation, or SLP, in tumor cells while enhancing OXPHOS efficiency in non-tumor cells, normal body cells, offering a therapeutic strategy for managing most cancers. Ketogenic metabolic therapy will also reduce the lactate succinate acidification of the tumor microenvironment, which can block the efficiency of immunotherapies or even just your immune system. And that tumor microenvironment leads to metastatic spread as well. The glucose ketone index was developed for estimating the degree of therapeutic ketosis by measuring the millimolar ratio of glucose to ketones, beta-hydroxybutyrate, in circulation. Therapeutic ketosis will enhance OXPHOS efficiency in normal cells while lowering glucose availability to tumor cells. In general, the lower is the GKI, the slower is the tumor growth. I may have altered where the location where is there, but it is what it is. This is important because aggressive tumor growth and poor patient survival are linked to elevated blood glucose levels in a variety of cancers. Ketogenic metabolic therapy can also be used together with other therapies, including standard of care, if efficacy can be maintained with no or minimal toxicities. I'm guessing what they mean there by that is that, and maybe, some of you guys can chime in the chat, but some of the therapies that are used in conventional medicine, the most obvious one would be glucocorticoids like dexamethasone or prednisone, can completely derail your ability to get into ketosis, right? Because it's going to create massive amounts of hyperglycemia. It's going to raise insulin. It's going to lower your ability to make ketone bodies, right? And then there's some chemos that can also seem to have an effect on being able to get in ketosis. And then at least one person on this live stream, I won't name names, knows that androgen deprivation therapy also seems to make it difficult to get into therapeutic ketosis, because when you have no testosterone, that can decrease your ability to handle glucose. And that's well known. So yeah, there are a lot of different therapies that are within the standard of care that can affect the efficiency and make it impossible to maintain efficacy of ketogenic metabolic therapy, and what I would maybe consider as a toxicity, a different way of looking at toxicity, right? So it begs to know what you're being put on and know what the effects, because I guess you would call hyperglycemia, hyperinsulinemia, a side effect of glucocorticoids like steroids, like prednisone, like dexamethasone. But in some ways, it's not really a side effect, because that's what it's supposed to do. It's basically cortisol, right? So you need to know how the standard of care may affect your ability to even undergo ketogenic metabolic therapies. I think that's important. I think that's an important distinction, clinical distinction to make, actually. So they have a new graphic in this paper that I think also is pretty cool, which will probably find its way into one of my courses or one of my other slide sets, because why not? It's a beautiful graphic. So we have glucose here, and that is, so this is the, I thought this was going to be the side of the cell membrane, but this is actually the mitochondrial membrane, because I'm seeing that this is cytoplasm, mitochondrial matrix. And we see the PPP here, which is also part of the cytoplasm, and of course glycolysis is part of the cytoplasm as well. So we see glucose, and we see a big thick black line here that's undergoing glycolysis and getting turned into pyruvate. Under normal circumstances, pyruvate is going to be converted into acetyl-CoA and then go through the TCA cycle. And then the TCA cycle is going to put off NADH and FADH2, and that's going to go to the electron transport chain and make energy that way, right? That's normal physiology. This is a cancer cell, so it's not doing that. So we see a big, thick line here, and we see that going to either the PPP, the pentose phosphate pathway, which is what's responsible for making all kinds of things, including nucleic acids for DNA and RNA synthesis, right? Also, the recycling of our thiol antioxidant systems like glutathione, et cetera. And then we have pyruvate going to lactate, and lactate then being transported outside the cell, extracellular space, to then set up the acidic tumor microenvironment, right? And then we have the electron transport chain, and we have glutamine. We have the TCA cycle, and we have glutamine being converted to glutamate through this GLS enzyme, then glutamate being converted to alpha-ketoglutarate via the glutamine dehydrogenase enzyme. It's also sometimes in other graphics shown as GLUD instead of GDH. And then then alpha-ketoglutarate is going to be converted to succinyl-CoA, and this is where mitochondrial substrate level phosphorylation is happening, right? Succinyl-CoA to succinate, ATP, right? And then succinate, unfortunately, will then go outside the cell to at least partially acidify the tumor microenvironment, just like lactate is, inhibits the immune system, inhibits chemotherapy from working, et cetera. Succinate also acts as an oncometabolite. It actually will stabilize hypoxia-inducible factor. And if you've listened to anything about me talking about hypoxia-inducible factor is responsible for upregulating everything related to glucose and glutamine metabolism. So that's not good, right? And so this is what we're left with, right? And so what we see here is ketogenic metabolic therapy is blocking the amount of glucose getting to the cell. So that way it's lowered amount getting to the cell, and it can't participate in all this stuff here, right? Then you could argue that ketogenic metabolic therapy also is going to look at glucose inhibitors, right? Because that's part of Seyfried's graphic, right? Glucose inhibitors, right? So you could argue that maybe there's not enough space here in the graphic, but glucose inhibitors. There's even inhibitors of glucose 6-phosphate dehydrogenase, so we can shut off maybe the PPP, although stopping glucose from getting into the cell or higher up in the process like hexokinase is probably a better strategy. And then we see ketogenic metabolic therapy over here as well, because it is taking care of glutamine as well through the inhibitors of glutamine, right? We have multiple targets here. We have the glutamine transporters, we have glutaminases, we have glutamine dehydrogenase, even have some of these enzymes in here. This is where ivermectin, for example, will downregulate succinyl-CoA synthetase here. And then you see a little KMT here, right? With a little arrow here. And what it's saying here, and this is interesting, we talked about this in the ketones lecture, where the ketone bodies will actually steal CoA and succinate away from this reaction that makes ATP. So it actually kind of, they believe that the ketones will actually steal succinate, succinyl-CoA away from these reactions that make ATP so that they can be then metabolized. And you actually end up kind of losing energy in the game for cancer cells specifically, and not for normal cells. Normal cells, you know, this would then continue on and actually make energy even more efficiently, like it mentioned there, right? So this is the new graphic that Seyfried and his group has put out, which I think highlights, and it really kind of is a culmination really of what we've looked at in this entire paper and our digressions into ketone body metabolism and how glutamine can't, you know, be replaced by any other amino acid because it's a losing some gain, because you actually end up losing more energy than you gain in the back in this step here. So that is what is proposed, right? And that's kind of where they don't have any more graphics, you know, that are more detailed. You know, that's where we would go back to the December 2024 paper that I did a couple of live streams on, and we went over the entire paper where we look over, you know, the way that you functionally, and I dare say clinically, handle this. And they do a beautiful job of laying out what a ketogenic metabolic therapy strategy could be, you know. And really every doctor who's open-minded, who does integrative or functional medicine and has any cancer patients should be handed that paper, because it's so good. There's things that I think that are missing from the paper. And I think that because we are in the position that we are really like going through these papers with a fine-tooth comb, and we're like trying to like even do super metabolic therapies, because we're leaving no stone unturned in any area of science, trying to enhance the basics, right? But this is the basics. And this is required reading as far as I'm concerned. If your doctor has not seen this paper, get it to them. And if they refuse to read the paper, I might find somebody else. All right, so they continue on here. While the elevation of circulating ketone bodies allows for the chronic restriction of glucose availability, glutamine availability cannot be chronically restricted due to the importance of the urea cycle, gut health, immune function, etc. Consequently, glutamine targeting should be pulsed rather than pressed to avoid adverse toxic effects. To use a pun on the words here, I did press Dr. Seyfried about this, and I gave him my opinion about this, and we have a discussion in our podcast about this very issue, because I do believe personally that glutamine can be pressed to some degree, and we talk about it. Let's just put it that way. Cells of the immune system, especially macrophages, use glutamine for energy and other biological functions, including wound healing. Most metastatic cancers also express biomarkers of macrophages, indicating that macrophage/myeloid origin of metastatic cancer arising from either direct transformation of a macrophage myeloid cell from a fusion hybridization between neoplastic stem cells and macrophages. In other words, the same fuel driving metastases is also needed for supporting immune cell function. These findings indicate a strategic glucose-glutamine targeting will be necessary for managing invasive and metastatic cancers while maintaining normal immune cell function. It later says here that it is important, it is interesting also that some parasites, like tumors, rely more heavily on substrate low phosphorylation than oxphos for ATP production. These findings could make parasite medications potentially non-toxic, cost-effective treatments for managing cancer, including pediatric high-grade gliomas. We have suggested that targeting oxphos might be also effective in managing cancer. Serious toxicity to normal cells could be an unanticipated consequences of such therapeutic strategies. Okay, I thought it said we were doing it. Okay, while some have suggested targeting oxphos. Okay, that makes more sense. Sorry, I got a little off just reading that. I was like, wait a minute, Seyfried is recommending this? I don't never see him say that. So they're saying while some people have suggested that targeting oxphos might be an efficient or effective way of managing cancer, serious toxicities to normal cells could be an unanticipated consequence. True, right? Because we are anticipating that the normal cells, non-cancer cells, can use oxphos and use ketone bodies. And so therefore, if we cut off oxphos or for normal cells, then that would probably actually have more of a profound effect on the normal cells, knowing what we know about cancer by metabolism than the normal cells and the cancer cells, excuse me. It is in our view that simultaneous targeting of glucose and glutamine while transitioning the body into nutritional ketosis will stress tumor cells of the energy and the carbons and nitrogen needed for the synthesis of growth metabolites. This therapeutic strategy will also reduce the acidification and inflammation of the tumor microenvironment, thus facilitating the non-toxic management for cancer or of cancer. So that is their therapeutic implications by what we're seeing here, which I think we all, or most of us who've been watching the channel for a while, can agree with. Let's go to the conclusions. Let's finish this paper out. Scientific theories are simply attempts to explain the facts of nature. Reality is based on replicated facts, whereas the interpretation of these facts is based off of credible theories. While Warburg was largely correct in recognizing oxphos insufficiency linked to compensatory lactic acid fermentation as the origin of cancer, several questionable assumptions and measurements of cellular ATP production have confounded data interpreted links to his hypothesis. Warburg's reliance on oxygen consumption rate and lactate production as measures to support his hypothesis were inaccurate and contributed to confusion in biochemical terminologies, which persist even today in the cancer metabolism field. Moreover, he did not know that glutamine-driven mitochondrial substrate low phosphorylation through the glutaminolysis pathway could also contribute to cancer cell ATP production. These issues have now been better clarified. While the somatic mutation theory is currently the predominant explanation for the origin of cancer, the mitochondrial metabolic theory offers a more credible explanation that can lead to more effective and less toxic therapeutic strategies for managing cancer. Pretty good. Pretty good. That paper, I mean, the last few papers that Seyfried and his group have put out, man, starting with the glutamine one they did in November of 2024, the therapeutic strategies paper that came out in December 2024, and now this one, they are putting out really good work. They are doing excellent work up there. And all I can hope for is that they are allowed to just have free reign over this area of science so that they can continue to make important discoveries and to really hopefully push us in the right direction. Let's see here. Got some comments here. What is the contribution of acetate, as it is found elevated in several cancers, particularly in oral cancers? I hope you cover this in the future. Actually, I've covered it in the past, my friend. I have had a couple videos on do cancer cells use ketones for fuel, and I cover it in 2 videos. It's about, maybe an hour and a half of material. Maybe almost 2 hours of material. And I would highly recommend looking at that. I don't want to screw anything up with this live stream because I don't want to get out of this to see what the actual titles are called, but it's pretty straightforward. It's like, do cancer cells use ketones, basically, or something like that. Excellent, Dr. Peebler. Great way to spend the lunch. Knowledge is delicious. You're so right. It is overwhelming trying to figure out what to and not to do while changing my lifestyle, all while keeping up with everyday life responsibilities. I appreciate your dedication. I agree. I mean, I can't empathize completely because I'm not in your shoes, but I'll tell you that I can imagine what level of um, life is going to be turned upside down just by the simple diagnosis. And then once if you're able to get into this world, into this realm of mitochondrial metabolic therapy, et cetera, and now like you're like looking at, graphics that I think at this point I take for granted, but this is complex, like this. Actually, I'm out of I'm out of the. But this is complex. This is complex. This is complex. This is complex. I mean, I sometimes don't realize these things are so complex, and I just, I hope that I'm explaining it well, and not taking for granted that this is very complex. And I understand that that leads to probably more fear and hopefully less confusion, but maybe more confusion, and kind of another vicious cycle of what am I to do and what am I not to do? Is a plant-based, vegan, high carbohydrate, low fat, low protein diet the way to go if I have cancer? Like some influencers and some doctors online will say, is carnivore the way to go? Is this supplement the way to go? I can understand the confusion. I could see that. Are you familiar with the latest sugar diet trend and the Randall cycle? If so, a few thoughts. So the Randall cycle, I think I've heard of it, but I can't think out of the top of the head what it is. So I'm not going to comment there. I have to look it up and then be able to comment. But then what I will tell you is that I did a whole video when the whole sugar diet came back, I'll say, because I was aware of it when I was in medical school. I actually was a high carbohydrate, low fat, low protein vegan for a period of time in my life, based off of Caldwell Esselstyn's, the China study, all of those, and I was in that for a while. It personally destroyed my health, and I didn't have any real health issues. It really damaged me. And so therefore I exited that realm, was even a raw foodist, for a while, fruitarian. And so therefore I'm familiar with the sugar diet for years and years. It's now come back. And some of the same influencers that I used to listen to, 15 years ago are kind of coming back again. Maybe they never left, but they were kind of coming back into and then there are a couple of people that people I listen to, bodybuilding type shows, that was really getting into the sugar diet. So I did a video on it too, because I felt it was the right time, because people, unfortunately, they get into fads sometimes. And I did not want anybody in this area of medicine to get into that fad in particular, because of what we know about hyperglycemia, what we know about glucose, what we know about insulin, what we know about any of these stuff, right? And so I did a video about it. So I did do a video about that. I don't know if that's enough of a thought about it. What I'll tell you is that I personally believe that there are probably versions of diets that are high carbohydrate, that can be healthy if you don't have cancer, or some really severe metabolic, disease, because one of the things that I've learned in doing all of the deep dives that I've done is that people who have the highest amount of flavonoids in their diet do really well from a lot of conditions, including cancer. And I see that as a paradox, because when I looked at the USDA databases and I was figuring out what foods have the highest amount of flavonoids, other than spices, which is kind of a league of its own, and those spices you're not going to be taking large amounts of generally. So I don't really consider that a food. But foods that actually contain calories that you actually will eat sufficient quantities of, fruits have the highest amount of flavonoids, including especially berries. And there are levels within levels of berries that have higher flavonoids. And my point is that people who have high amounts of flavonoids are very high flavonoids. They can do well with cancer, from a mortality perspective. But those foods maybe also contain sugar. So my point is that there's always a risk versus benefit with whatever intervention we do. We know this in medicine. If I put you on a D5 drip, which is basically sugar, 5% sugar and water, I will cause hyponatremia for you, right? And if I put you on if I don't let you eat for days on end, I'm going to likely cause a problem, right? Like so, or if I starve you of water, just feed you, right? Like that will likely cause hypernatremia and cause another problem, right? And those are just simple examples with like something like water, something simple as water. So there's always going to be a risk versus benefit with whatever intervention we do. And so therefore, like I think that you can have a more balanced approach before a diagnosis of cancer. But when you have a diagnosis of cancer, if you want to use the best of what science has for you to succeed with that diagnosis, then I think that an all sugar diet, like what I mean is like some people are like pouring sugar into smoothies, right, with bananas and dates. I think that you would be probably doing yourself at minimum a disservice, right? But you're probably going to be actually hurting yourself because you're going to give the cancer exactly what it wants. And the glutamine, of course, it can make its own. So therefore, I think it would be a really bad idea for this area of medicine to be on a sugar diet. And I'll leave it there. Watching from Saudi Arabia. Well, welcome from Florida. Well, that was my question. The overconsumption of sugar cause cancer or should be avoided once you get it? I will have to track it down that video. Thank you. You're welcome. That's like probably $1 million question. And does high sugar cause cancer? Wow. I think you could easily make the argument because and I think you have to also have a lot of nuance, because if you're saying that like sugar is obviously the simple carbohydrate, the 6 carbon molecule, and when people say sugar, they can also mean high carbohydrate, right? And then you're like, well, where does the sugar come from? Is it coming from like black raspberries, or is it coming from table sugar that you pour into your food? You know what I mean? Like, I think that there's a lot of nuance there. What I'll say is that hyperglycemia, high blood glucose, absolutely is inflammatory and absolutely can damage mitochondria. Hyperglycemia can stabilize hypoxia-inducible factors. So there's a lot of things that you could see that could be very negative about a high sugar diet. Sugar, and when I mean sugar, I mean truly sugar. Negative. And so therefore, I think it would be a really bad idea to have it do that before, cancer. After cancer, it's like just an absolute no. That's with an exclamation point, underlined, bold. Like there's no way to really justify that once you have a diagnosis of cancer. But why wait until you have a diagnosis of cancer to then make that decision? Because then I don't know. One of my favorite sayings was, I don't remember who coined it, but it was, an ounce of prevention is worth more than a pound of cure. Like we can have the best metabolic therapy possible, but if we can prevent it from happening ever, trust me, I'm doing you a service. There was also another story that I heard when I was in residency. It was really good. It was basically, you could have a tribe that lived on a cliff, and this tribe like would always, every once in a while they would lose a tribe member who would like fall off the cliff. They would be doing something and fall off the cliff. And so what the tribe did, or the town did, was they at the bottom of the cliff, they made the best ambulances, the best hospital, the best trauma center, right, to deal with these traumas that were coming in for these people falling off the cliff. And then they made the fastest ambulances, and they still were having people fall off the cliff and die from falling off the cliff. And really what the solution was just to like put up the fence, right, that would make people so they couldn't jump off the cliff or fall off the cliff, right? And I think that's a very good analogy to what we do. We have these beautiful, huge hospital systems, and we have beautiful, fancy ambulances, and we get to the hospital and we get you on the cardiac cath table in 45 minutes, and we initiate the sepsis protocol within so many hours, and it's just like that is the best we can do from that side of it. But the preventive side, we do almost nothing, and that's where we need to go. And I think that a sugar diet, obviously there's varieties of those sugar diets, and you can pick apart each one of them. But I think that's probably a really bad idea before you get cancer, and it's after you get cancer, it's an absolute horrible idea. All right, we've got an hour. We've covered the entirety of Seyfried's paper, and I am going to put out the first roughly half of the interview with Seyfried on Monday morning at 0900 Eastern Standard Time for you guys to watch. And then I'll put the other half roughly the next Monday. And we'll go from there. And I hope that you guys enjoy the interview. I'll tell you what, he's a little bit my hero, in some ways. Obviously, he's a big figure and a big influence on the channel here. And it was pretty surreal to meet him. He was in his, I'm sure most of you have seen multiple podcasts with him. He's always in that same, background in that same office. So that was kind of surreal. But he could not have been nicer. And he could not have been more down to earth. And, if there's something that I took away from it, was that he really has a disdain for the system that impedes metabolic therapy from being more readily available. And he really wants people to get better from cancer. If there's two things I took away from that, that would be it. He really does not want people to have cancer and not want to be subjected to, toxic therapies when we have non-toxic, potential therapies potentially at our disposal. They're not always at our disposal because of the way it is. But it was a really good conversation. And I really look forward to talking to him again at some point, God willing. And there's other people in his lab that I would like to talk to, one of which has already kind of committed to doing it. And there's many other people within the field that can give us answers that I don't have, that we don't have as a group, that the literature maybe doesn't have, and that we can have these experts kind of speculate based off of their expertise, which can help maybe move us forward in our understanding and our knowledge. The last person said, what would be your own best, what I eat in a day if I had cancer, everything you would eat in a week? Well, I don't think I could probably say that today. But I will tell you that my answer would be more nuanced than Dr. Seyfried gives. His answer would be just keep your GKI as low as possible, right? And I think that there's actually quite a bit more nuance to the recommendation than that, because of the phytochemicals and compounds and vitamins and minerals and fatty acids and different things that you need and can't make, but also things that you can help fight against cancer and lower cancer-related mortalities. So therefore, I have my own personal recommendations that I give, and it's changing, kind of ever changing based off of new data and literature. But I do that in consult and I do it in courses. But I don't generally give clinical advice, over the internet, in this kind of a format. But I'll tell you that keeping your blood glucose less than 80 and keeping your GKI of 2 is definitely part of the framework, right? And that would be considered a therapeutic ketogenic diet. And there's probably a lot of influencers on various social media channels and that have really good insights into how to structure a therapeutic ketogenic diet and what foods even to eat, and probably make it even palatable. Because, I'm really interested in biology and graphics like this, but I'm not a chef or a cook. So therefore you're probably not going to want my recommendations anyway. But I do have lists of foods, for example, that I think could be beneficial to help, as an overview. I don't know if that helps or not, but for fats, do you recommend saturated or unsaturated? I guess both, because what is olive oil, or what is avocado or avocado oil? That's a mono unsaturated fat, right? What is effectively omega-6 and omega-3s? Those are polyunsaturated fatty acids, right? So, and then of course, butter and ghee and coconut, those are generally saturated fatty acids, right? So I would say all of them. It's just that, I don't want you over consuming omega-6, for example, because that can be somewhat pro-inflammatory and throw off your omega-3 omega-6 ratio. And that's more kind of clinical answers, that that we can give in a consult. But I would say that really any of them. The only thing I would probably straight up avoid would be, trans fats, which is kind of like a processed fat. And then I'm not a huge fan of like having a lot of omega-6, like I said. Otherwise, I think it's free game. Of course, I would always rather it be part of a whole food and not as a processed oil, in general. The only oil that I'd probably be okay with would be like cold or ice pressed, like extra virgin organic olive oil with high polyphenol content, because it's been shown that olive oil consumption can lower mortality upwards of 50 to 60%, depending on the amount that you use. So that's pretty big, right? So that's about the only oil that I recommend, other than maybe MCT oil, which is like a purified C8 or C10, coconut oil or something like that. So those are the only oils I would say, but generally whole foods otherwise. All right. Got a little nutrition aspect to this. And I think it dovetails nicely. We're talking about ketogenic metabolic therapy, right? We're talking about, therapeutic ketogenic diets and keeping your GKI low. And what's going to do that is going to be a high fat diet. So, all right, well, we've got an hour and 7 minutes. I am going to go have, I guess, breakfast for me. So if you like videos like this, please like, share, and subscribe. Until next time.